Yes, the wealth inequality is crazy, but you know what else is crazy? Cross entropy. All right, so far we've gone over the surprisal factor and specifically information and how surprisal factor is the quantification of information. And we showed how that is by this equation of I as a function of probability is equal to negative logarithm of probability. And again, we use base 2 because of that beautiful math that we showed where each time the probability halves, the surprisal factor increases by 1 when we have base 2 on the logarithm. Then we went over Shannon's entropy, which is essentially telling you the average amount of information or the average surprisal factor from a whole source of information. Because obviously information isn't just going to be given, one piece at a time, it's going to come from an entire source. And that's how we went over Shannon's entropy right over here. Do that right there. So today we're going to be talking about cross entropy, and you're going to see how this all comes together. And this is the formula for cross entropy over here, and you might have no idea what this means, and that is totally fine because we're going to go over it. So first, let's think about an AI model and how it might be learning from the world and how it might be making predictions. Let's say our model is a weather model, right? And let's say on the training data set, or just let's say nature, right? Let's say the true possibilities or true probabilities is that sunny happens 80% of the time, or 0.8, and rain is 0.2%, or sorry, 0.2 or 20% of the time, correct? Because again, the world doesn't run on yes or no. It's just not binary, right? Everything runs on probabilities, right? So let's say this is the actual truth, right? And let's say we have an AI model, right? And let's say it predicts the weather to be, so let's do pred, right? And let's say it predicts it to be sunny as 0.5 and rain as 0.5. So that means it's pretty 50-50. So how would we go about actually measuring, the difference between the predicted and the actual one? Because obviously we're trying to minimize the difference between the predicted and the actual true probabilities when we're training an AI model. That way, we're able to reduce uncertainty, aka entropy. So how do we go about this? Well, a very simple answer would be to make it almost into like a distance formula, right? Where we subtract, the values and, go from there. However, that doesn't necessarily work because imagine if the true value is sunny at 0.99999, it's basically 1, and the predicted is sunny at 0.5. Well, then the difference is only going to be 0.499, but in reality, the difference or the difference or what we want our model to know is way larger because it made a huge issue. So that's not going to work. So what do we use instead? Well, we can actually use the surprisal factor instead. And we can use it and essentially just plug it in with our normal entropy, right? Because our normal entropy is essentially for one data stream. Now, cross entropy is going to be entropy but crossing between an actual and the predicted, right? So let's see how this works. Well, what we do is we write H, right? That's entropy here, or loss as it's called. And that's going to be a function of P and Q, right? So P is going to be the probabilities or the true probabilities, right? We can put true here, right? And Q is going to be predicted probabilities, correct? So these are the true probabilities and these are the predicted probabilities of our model, right? And we can just sub in essentially what we already have with Shannon entropy and instead just use, well, what we have here, what we have given to us, right? So with Shannon entropy, what we have is the probability, right? And then I of P, right? That's literally all it's saying. It's the same as saying correct? It's the same as saying that. So let's plug it in, but using what we have here. So this would render us with negative, and I guess this would actually not have a negative sign up front here. Let's do this, and let's do this to be P, right? P is going to be all of our true probabilities, right? And let's say this is x and we have px, right? Because obviously in our probabilities here, right, we have sunny, rain, right? Or imagine if it's like an animal classifier, model, right? Living image classification, right? It could say something is like there's a 90% chance it's a cat, there's a 5% chance it's a dog, like there's a 4% chance it's a donkey, right? That's going to be three probability features over there, right? In this case, we only have two. So that's what our x is representing, the feature essentially. So we have p of x over here, right? And then we put over here, we put not I. We have over here I of p, but I of p is just going to be equal to this over here, negative log 2 of p, right? But the probability that our model gave here is represented by q. So we just plug that in over here. Negative log base 2, again, this is coming from I of p, of q of x, right? Because q of x is our true, or not true, q of x is our predicted one, right? So we're rendered this, and we can take the negative sign out front to get us this. And that is how we go to cross entropy, right? So again, cross entropy is measuring the difference. So think about this in the context of AI models. Well, clearly, we are trying to minimize cross entropy, right? We are trying to minimize the distance between our AI model's predictions and the actual values that are in our training data set. So then, when we run predictions and we actually run our AI model, it gives us output that is very close to what it is trained on. And that is how cross entropy works. Now, now that we know about cross entropy, I'm just going to go into like a little bit more detail on Shannon entropy, because there's like this cool thing with Shannon entropy that you may have recognized. So imagine with Shannon entropy where we have like a scenario, right? Let's say our scenario is we have an input stream, right? And we have A, B, C, D, A, B, C, D. Okay, this is our input stream over here, okay? You see that each of these characters occurs twice, meaning each of these characters has a 1/4 chance. Well then, the Shannon entropy, well, it's actually really, really easy to find because all it's gonna be is just log of n, right? Log of n, which is going to be 4 in this case, when there is 4 separate different symbols. Log of n, right? So in this case, it'll be log base 2, which is going to be equal to 2, right? And that's the Shannon entropy whenever all the probabilities are equal. And yeah, that's just something pretty cool that I thought of. But yeah, that's cross entropy used everywhere.